Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the first tutorial for this week. And as you know, this problem asks you to show that this expression for the spectral function, which we obtained in the regular lectures, we obtained that A is equal to this. What we want to show now is that that expression is equivalent to these other two equivalent expressions. See? So what we want to show is that that can be reduced to that using just matrix algebra. So it is just an identity, that part. And the starting point is the first equation though. That is, GR is related to H and sigma by this first relation, and making use of that, what I'll show is that if this is true, then this must also be true. Okay. And just for reference, let me remind you that gamma is this I sigma minus sigma dagger. That's the definition of gamma. It's the anti-Hermitian part of sigma. Okay. So first we start from this retarded Green's function, which is the inverse of that. So I'll turn it around and write it as inverse of the retarded Green's function is equal to what's on the right hand side. So we'll write it like this. GR inverse is equal to EI minus H minus sigma. That's it. Now what we do is we take the conjugate transpose of both sides. So GR inverse, and then we take conjugate transpose, which is what we write as dagger, and that's then equal to conjugate transpose of what's here. Now, EI, of course, when you take conjugate transpose, it's still EI. H is Hermitian. What that means is it's equal to H dagger. But sigma isn't Hermitian, so when I take its dagger, we get something different. Now, the next thing is that GR inverse dagger is the same as GR dagger inverse. Now, this isn't obvious. Takes a little. You have to prove this, and I'll do that in a minute. I'll explain why. When you have a matrix and you take the inverse and the dagger in that order, you can reverse the order and you still have the same thing. I'll prove that in a minute. That's true of any matrix. Okay? But if you accept that, then the point to note is that that's equal to EI minus H minus sigma dagger. Same thing here. And conjugate transpose of GR, that's what we have called GA. See? So instead of GR dagger, then I could write GA. Okay. So those are the two relations that I need. The GR inverse is that, and GA inverse is that. And once we have those two, what we'll do is from those two we'll get the desired relations. But first then, let me prove that you can take any matrix, and if you have it inverse and then its dagger, it's equal to M dagger inverse. And this is true of any matrix. So let me just prove that. And the way I would do it is something like this, that take any matrix, multiply it by its inverse, that's equal to I, identity matrix. Now let's take dagger on this conjugate transpose on both sides. Of course, identity matrix, conjugate transpose, it's still identity matrix. Okay. Now when you have any two matrices conjugate transpose, so A, B dagger is B dagger, A dagger. So you could write this as M inverse dagger M dagger equal to I. So AB dagger is B dagger and then A dagger. That's it. So now the point is that since this times this is equal to the identity matrix, this must be like the inverse of that. So what this means is M inverse dagger must be the inverse of M dagger. So that's exactly what I was trying to prove, if you look back here. That inverse dagger is like dagger inverse. Okay. So that's the thing I used in getting from here to here. Okay. So now that we have these two, what I can do is subtract this from this. So what you'd have then is GA inverse minus GR inverse is equal to this minus this, and you'll notice the E and the H just cancel, and you get sigma minus sigma dagger. That's it. Okay. So now what I can do is I can multiply. Actually, I could replace this quantity with gamma, because as you know, sigma minus sigma dagger is like minus I gamma. So I could write minus I gamma here. Okay. So now what I'm going to do is we will multiply this from the left with, let's say, GR, and from the right with, say, GA. Okay. So we're multiplying with GR from the left, multiplying with GA from the right. So the first term, what will happen is GA times GA inverse, that's just I, so I just get GR. Minus, here GR times GR inverse, that's just identity matrix, and I get GA. And that's then equal to minus I. Remember, I took the gamma. If I multiply with GR and GA on the left, I have to do the same on this side also. So I'll get a GR here and a GA there. See? And now I can take the I from there and put it on this side. So minus I can divide by minus I, which means like multiplying with plus I. So you see, GR gamma GA is equal to I GR minus GA. So we have kind of done that second one. We've shown that GR gamma GA is I times GR minus GA. Okay. Now, how would you get the other property, namely the GA gamma GR? Well, the way you could do this is, when I said multiply from the left with GR and multiply from the right with GA. Instead, let's multiply from the left with GA and multiply from the right with GR. So what that means is, on this side, I'll get a GA here and a GR there. But on the left-hand side, you see it makes no difference, because GA inverse gives me I, and I just am left with the GR. And GR inverse gives me I, and I'm just left with the GA. So, I times GR minus GA is equal to GA gamma GR, and I had already proved a minute ago that this was equal to GR gamma GA. Okay? So, that completes this whole proof. That is, in my regular lecture, I had argued that A was given by this, and what I just showed is that if relation 1 is true, note that in this proof all I used was 1, that if 1 is true and gammas were related to sigmas in this way, then this is an identity. All three forms must be the same.